Greetings and welcome, friends. Mr. Waddy and, of course, my favorite geometricians, my class, are here today. We're talking about properties of trapezoids and kites. Zoinks! Wow, here we go. So it says a trapezoid is a quadrilateral with exactly, keyword. Oh man, keyword, exactly one pair of parallel sides. So does that mean a parallelogram is a type of trapezoid? Parallelograms are not types of trapezoids. Okay, it has a trapezoid has exactly one pair of parallel sides. The parallel sides are called the bases. Base, right? It says the base angles of a trapezoid are two consecutive angles whose common side is a base. So these two are base angles over here, and these two are base angles over here. Not necessarily congruent to one another. All right. For example, in trapezoid, abacadu, A and D are one pair of base angles, and B and C are another pair. So A and B are consecutive to one another, but they are not sharing a base side. The non-parallel sides are called the legs. Right? Somewhat like the legs of an isosceles triangle. Or actually, base, legs. Yeah, hypotenuse, yeah, there we go. If the legs of a trapezoid are congruent, then the trapezoid is called an isosceles trapezoid. That's interesting. It's interesting. Hey guys, we've got a pair of parallel lines cut by transversals. I bet all of our properties regarding parallel lines probably apply. I'm guessing. Let's see. Let's get to example 1. My friends in real life here with me are already got there. Let's see. What? Example 1. So it says, identify a trapezoid in the coordinate plane. Show that ORST is a trapezoid, then decide whether or not it is isosceles. So what can I do to show this? All right, it looks like we're missing a side of it right here. Kind of not showing up. All right, slopes would be helpful. All right, so slope formula, m is equal to y2 minus y1. You guys got that memorized, over x2 minus x1. So let's find the slopes, or actually better yet, let's just read the slopes right off this graph. Up 1 over 2, so the slope of rs is 1/2. And the slope of this one is up 2 and over 4. So the slope of OT is going to be 2/4 or 1/2. Therefore, I would say that RS is parallel to OT because they have the same slopes. Now, that does not technically prove that it's a trapezoid, because what if the other two sides were also parallel? And so you can notice here that RO is vertical. RO has no slope, whereas ST has a slope of, looks like down 2 over 2 or down 1 over 1, -1. And so these are not parallel sides to each other. So it is a trapezoid. Trapezoid. Oops. It is a trapezoid. Then decide whether or not it's isosceles. How could I do that? Yeah, distance formula is a great thing for finding distances and comparing them. X2 minus x1 all squared plus y2 minus y1 all squared. Then root that whole thing. Root a bega. All right. Actually, this one we could just find the distance just by looking at it. That's 3. All right, so RO equals 3. And let's find the distance of ST. So ST is going to be the square root of, I'll do 4 minus 2 squared. You guys are good at the distance formula, right? 2 minus 4 all squared. The order doesn't matter as much for distance formula, because if it's negative, the square makes it positive. So 2 squared is 4, plus -2 squared is 4. So it's going to be the square root of 8, which I can reduce That breaks into the square root of 4 times the square root of 2. And the square root of 4 is 2. If you need help practicing your reducing radicals, you can do that. So it is not isosceles. Not isosceles. Right? It looks like that's what I've concluded about this shape. Yeah, much easier to read the equations or the slopes off of a graph than it is using the slope formula a bunch. And that's what I'm a fan of doing, guys, trying to find the most efficient way to do some of these, right? All right, here's some properties. Trapezoid base angles theorem. Ooh, let's see, we got 3 theorems coming at you about trapezoids. Let's see, I don't think I can line this other one up just right. And I think it's bigger than the others. Or was it smaller? All right, we'll call it. Bam. All right, so it says the base angles theorem. When did we have base angles theorem before? That was with triangles, specifically isosceles triangles, in which we said, right, if you have an isosceles triangle, that the 2 angles opposite of those sides are congruent to each other. Right. And the base angles converse said the converse of that, as one might suspect. So it says, if a trapezoid is isosceles, then each pair of base angles is congruent. Each pair, both of them. All right, so these 2 guys and those 2 guys are congruent as pairs. Tell you what, let me see if I can do a quick geometer sketchpad sketch. All right, here we go. All right, so I'll make one side. I want this to be a trapezoid. So this leg is not going to be parallel. So how do I construct parallel? Well, I got to select a side and that, and I'll hit construct. You guys are all masters at Geometer Sketchpad, right, Anthony? Now, how could I make sure that this other leg is going to be congruent to this one? Josh, what are you thinking? You don't know. Yeah, it's a little bit tricky. Imagine using a compass, all right, where I could have measured that length and then stuck one end there and swiped it with a circle. So what I'm going to do is I'm going to construct a circle with that as the center and this as its radius. So construct a circle by center and radius. And if I now draw this piece right here, this would just be a regular old trapezoid. It's also possible to have like a right angle trapezoid. But now this is one where those, oh, I think it snapped off of it. There we go. I'll just do it that way. Bam. Like so. And let's see. Well, oh dear. Oh dear. What did I do? All right. Let's snap from that to that. Snap. Oh, snap. Control H is your quick hide, by the way. So here, now I've got a series of isosceles trapezoids that I can make. And what we were arguing was that the base angles are congruent. So I'll measure the angle. And would you look at that? Would you look at it, friends? Those angles are definitely congruent with one another. Now, because these are 2 parallel sides, I'd also expect that these 2 angles, non-base angles, are supplemental to one another because those are consecutive interior angles. But let's figure out those angles as well. Measure angle, and I'd expect that angle D will also be congruent. Right, and no matter how I arrange this, notice how that works. Let's see, can I break this one? Oh, yeah, I broke it. Yeah, once I go obtuse, then it breaks it. Whoa, yeah. I like breaking my sketches here. So, base angles theorem works. Also, the base angles converse. If you have 2 angles in a trapezoid that are base angles and they are congruent, then the legs of the trapezoid, it's going to be an isosceles trapezoid. Now, this one's interesting. When did we... Oh, okay. What quadrilateral had congruent diagonals that we already talked about? No. Parallelograms, diagonals, what? Bisect each other. A rectangle's diagonals are congruent, and then all subcategories like squares would also... That's the only other subcategory, I guess. Yeah, so rectangles had congruent diagonals. It turns out isosceles trapezoids do as well. Let me just draw this real quick. and then I'll move on. I won't draw the sketch for the other shape for the kites that we'll be doing in a minute. And let's see if I can measure these diagonals. Measure lengths. Would you look at that? They're the same, except when I break it, right? But yeah, so it's a thing of beauty. Oh wow, I can invert it on itself. That's weird. So yeah, so isosceles diagonals, or isosceles trapezoid diagonals theorem. Yeah, that works out just great. So these properties are, you know, I think pretty simple to see, a little bit harder to prove, and then I think application of them is pretty easy as well. So here's like a, looks like a keystone on an arch. I don't know if you guys knew that was called a keystone. Either of that or I'm making it up. It says the stone above the arch in the diagram is an isosceles trapezoid. Bam, I agree. Find the measure of K. All right, well, these base angles are going to be congruent, so measure of angle K is going to also equal 85 degrees. How can I find the measure of angle J? Okay, all four. Wow, I didn't even think of that. You're right. All four of these are going to add to 360, so you could use the corollary of the polygon interior angle theorem. Or you could use the fact that these are consecutive interior angles and use that since those are parallel lines cut by a transversal. So the measure of angle J is going to be, looks like 95 degrees, right? Because that plus that is 180. Good, right? So yeah, application of these, pretty straightforward. Ooh, mid-segments. Man, we're having a good day today. Mid-segments. All right. Wow, I like this. I like this. All right. For a trapezoid, it says the mid-segment of a trapezoid is parallel to each base. All right, so a mid-segment is going to connect the midpoint of the two legs. All right. And it's going to be parallel to each base, and its length is 1/2 the sum of the lengths of the bases. Let's just call that the average. Right? Add them up, divide by 2. That's just called an average. Yeah, so that's pretty cool. Also, it's interesting. Maybe one day we'll do a sketch where we have a trapezoid, and then we'll make the length of AB get infinitesimally small until it becomes a triangle. And then, like, triangle mid-segment theorem can morph into trapezoid mid-segment theorem, and it's pretty amazing. So yeah, so the length of this mid-segment is the average of A, B, and DC, and also they're all parallel. I was going to ask you whether or not these two small trapezoids are similar to each other. We haven't talked about a lot of similarity yet, but what's your hunch? I could show that this angle and this angle are congruent. They've got all similar angle, congruent angles. Yeah, this one is stretched out more than that one. Yeah, so these two trapezoids would have congruent angles by using some of our parallel line properties. But these are not similar trapezoids to each other. All right, not similar trapezoids to one another. Okay, pick up the pace. Let's see if we can get some class questing today. I guess we already did quest a little bit together. All right. Using the mid-segment of a trapezoid in the diagram, MN is the mid-segment. Find MN. All right, MN is just going to be the average of those two, right, Malik? Add them up, divide by 2. I'd rather write it like that than the way they were doing it. So it looks like 40 divided by 2. Looks like MN is going to equal 20. All right. And also, we would know that MN is parallel to those because of trapezoid mid-segment. I was going to say triangle. You almost got me there, friend. All right, we can also apply these properties on a coordinate plane. And when we're dealing with a coordinate plane, you're going to be interested in slope formula. You're going to be interested in distance formula. Midpoint formula is how I could even find the location of y to begin with. So it says find the length of the mid-segment. I don't know where y is. All right, sure it looks like we could read it off the graph, but I could use midpoint formula to find those. Tell you what, let's read y off the graph and we'll find z that way. So what are the coordinates of y? Oh, wow, with the scale change, and you guys didn't make that mistake. So it's 4, and then how high is that? 8. Okay. Let's find the value of z. I think we could guess it, but let's not do that. Let's actually find the midpoint. So z is going to be the midpoint. I keep using equal signs there. Of those two, so that's just the average of the x's and the average of the y's. Right, you guys have done all that before. So z is going to be 12 plus 2 is 14, divided by 2 is 7, and 2 plus 2 is 4, divided by 2 is 2. So 7 comma 2, which is what you might have expected from there. So those are the endpoints of that. But now they wanted the length of this. So to find the length, let's use the distance formula for yz. Right? And you guys are all experts at this. You've seen it 1,000 times. Right? You just plug it in. Plug in, chug, friends. 7 minus 4 is 3. 3 squared. 2 minus 8 is negative 6 squared. Let's see. So that's 9 plus 36. What's that going to be? 45. Can I reduce that? Radical? What's the largest perfect square that goes into 45? Perfect square. So like 4, 9, 16, 25. That divides into 45. 9 does. And the square root of 9 is 3, so 3 rad 5 is the length of that. And you could get decimal approximations if you would. Oh no, I did the zoom out. I broke space-time, friends. I'm sorry. Wow. All right, let's talk about kites. I was gonna say, let's talk about kites. I never read the book Kite Runner. It sounds like it's a sad book. Is it sad? Oh, man. I hear it's good, though. Is it something I should promote on my channel? I don't know. Yeah. All right, I hear, yes, my students say it's good. All right, so let's see. A kite, by mathematical definition, I'm assuming this was, I don't know, which was named first? Was the flying kite named after the shape, or was the shape named after the kite? That's a question for the internet. Internet! What is that? All right, they'll get back to us. That's how the internet works. It says a kite is a quadrilateral that has 2 pairs of consecutive, not opposite, consecutive congruent sides, but opposite sides are not congruent. All right, so that makes sense. It's a kite, if I ever saw one. You guys should do some Geometer Sketchpad with that someday. Maybe during an ACE. Give it a try. It turns out there's some properties with kites. In a quadrilateral, if a quadrilateral is a kite, then its diagonals are perpendicular. What other quadrilateral had that property? Rhombuses, right? The parallelogram who has diagonal perpendicularity. And it turns out for kites that you also have that. How about kite opposite angles theorem? If a quadrilateral is a kite, then exactly one pair, because if it was both pairs of opposite angles congruent, then we would have had right, parallelogramness. We've already know that. That's enough to prove a quadrilateral is a parallelogram. But here we go. It turns out that it's in a kite, exactly one pair will be congruent. I think I'll call this coat. I think that sounds good. Coat. I like it. All right, we're gonna skip the proof for now, but maybe during an ACE we can hang out. We could prove this. Yeah. Come and hang out. Proving things with the geometry. Look at that lovely kite. I love it. All right. Find the measure of angle D. Guys, what are your thoughts? I've given you a property. You have some previous skills. I've never shown you this example before or one like it. What could I do? Okay, so these two are congruent. We'll call it x degrees, maybe. I think that's with the setup. Oh, 360, that's right, because it's a quadrilateral. Let's see, what's that going to be, 188? Did I add that right? Yeah, subtract that from both sides. Oh, and I'm so used to writing 180. And let's see, so 2x is going to equal, I don't know if I trust myself. What's that going to be, 172? Yeah, you guys agree? All right. 172 it is. Divide both sides by dose. And looks like, well, if it was 180, it would have been 90. So it must be 86? I think so. And that is the measure of angle D and F. So 86 degrees is our answer. I guess I could write that in terms of measure of angle D equals 86. There you go. So you can use that property, and we used our properties of polygons as well. All right, I like this little chart of special quadrilaterals because we've got a whole other family now, a whole other family tree. Yeah. I should actually have, well, I could have you guys make your own Venn diagram of quadrilaterals, a whole bunch of nested families. So of quadrilaterals, we've got parallelograms, and within those we had rectangle, rhombus, and then squares was both of those. And then we also now have trapezoids and kites, and within the family of trapezoids there are isosceles trapezoids. Isosceles trapezoids. So now you can use these skills, and you can identify quadrilaterals based on what part of its family it's in. Yeah, so see if you could figure out, with all the properties we know, which we know a lot now, hopefully we do. I would recommend going back and reviewing some of those. Let's see, this says, what is the most specific name for quadrilateral ABCD? Let's have a conversation, friends. Is it a parallelogram? Okay, so in terms of the direction we're going into this category, which is eliminating these possibilities. Yeah? Okay. All right. Why is it a parallelogram? Both pairs of diagonals bisect each other. Like, yeah, it was like parallelogram, diagonals, theorem or something like that. Well, the rhombus, maybe, is it? I don't know, is it? Could this be a rhombus? If I knew that these were perpendicular to each other, it would put it in the rhombus family. Right now I've got this. I know it's a parallelogram. Is that as specific as I can get? I think so. I think so. I mean, we also could say a whole bunch more information about vertical angles and proving triangles congruent and all sorts of things like that. But I think we're good. All right, thanks for watching, friends. Bye-bye.